Good morning, everyone. Welcome to the NJIT Technology and Society Forum Series. I want you to get an idea of who it is who's been actively involved in bringing these excellent speakers on these important topics to NJIT. Jay, you want to stand up? And Jay's the ringleader of the group. Great. And I know there's a number of others who are active members of the committee. Can you just stand up? Nancy, you part of it? Who else? Up here? Oh, the front row bunch. It takes a bit of effort, so I know we all appreciate it. Some of you might know, I hope most of you know that I'm the provost, Priscilla Nelson, but some of you might not know that I'm by training originally a geologist. And I feel a kinship always during my days at National Science Foundation with the Directorate for Geosciences, which was so ably stewarded by our speaker today in the recent past. Geosciences at NSF has a long history of tremendously influential and stable leadership within the foundation, and our speaker today was no exception to that. Our Earth's systems are complex, interdependent, and interacting in ways we are only now coming to understand. We know the Earth's climate and ecology have changed profoundly in the past, and there's a growing awareness worldwide that the near future will bring major environmental changes of great significance for nations, social institutions, and for individuals. And we here very close to the waters of the Atlantic and the Hudson River feel that very acutely. Our speaker today is Dr. Margaret Leinen, who comes to us as the Chief Science Officer at Climos, a Silicon Valley startup that is working to understand our Earth's systems and to leverage natural processes to reduce greenhouse gases and mitigate climate change. Margaret holds a PhD in geological oceanography from the University of Rhode Island, an MS in the same field from Oregon State, and a BS degree in geology from Illinois. So she believes in moving around to institutions like I did. Prior to her recent appointment with Climos, Leinin was the Assistant Director for Geosciences at the National Science Foundation, where she led the transition of the ocean drilling program to the integrated ocean drilling program and oversaw the development of the Ocean Observatories Initiative, sometimes called OOI, in our inimitable way of inside of Washington, of applying three vowels together and getting a word out of it. I don't know how many places can do that, but we certainly could inside of Washington, D.C. And at the University of Rhode Island, Leinin served as Dean of the Graduate School of Oceanography, Dean of the College of Environment and Life Sciences, and Vice Provost for Marine Programs. She's a Fellow of AAAS and of GSA, which is not the Graduate Student Association of NJIT, but the Geological Society of America. While at the NSF, Dr. Leinen oversaw publicly funded academic research initiatives in ocean, atmospheric, and earth sciences in the United States. She also served as vice chair of the U.S. Climate Change Science Program, the interagency program responsible for coordinating federal climate change research. Dr. Leinen is a well-known researcher on her own in paleoceanography and paleoclimatology, where her work focused on ocean sediments and their relationship to global biogeochemical cycles in the history of the Earth's climate. And Dr. Leinen is a most excellent person to help us to understand the recent report by the United Nations Intergovernmental Panel on Climate Change, IPCC, that we've heard about so recently in the newspapers. So I invite you now to join Margaret Leinen as she explains how the buildup of atmospheric greenhouse gases over just 2 centuries has impacted the Earth's climate and ecosystems, and how changes we are experiencing cannot be modeled without including fossil fuel emissions. Leinin will examine the essential role of geosciences in understanding how climate processes will respond to a continuing increase in greenhouse gases and the rate at which the changes will occur. So I invite you to welcome our speaker, Dr. Margaret Leinen.
Thank you, Priscilla, and thank you to NJIT for the invitation to come and talk to you today. It's a real privilege to be able to talk about not only the science that has been done in this area, but talk at a time when this issue of climate change and global change are so much in the news. And I'm not going to focus entirely on the science and the record of what's happened in the science, but also try to cast that in light of the developing debate over global change, over climate change. I'm a very strong believer, especially in this area, that this is where science and understanding of the earth the rubber hits the road. We are facing very major decisions for the country, for the states, for our local governance, and as individuals about our economy, the way that we use energy, and our future. Science plays a very important role in that debate, but it is one of the elements of the debate. And I'd like to tell you a little bit about that from my point of view. So in the unfolding story of global climate change, there are 5 elements that play critical roles from a point of view of a scientist. Theory, understanding of Earth processes, that is going out and finding out how the Earth really works. Observing change, especially in this area of climate, we need long-term observations. Models, mathematical models of how the Earth works. And chance, and I'll tell you a little bit more about that. So just to put us all on very basic and common ground, there is a natural greenhouse effect that keeps the Earth warmer than it would be otherwise. And a little basic physics, if an object like the Earth is bathed in visible light, it warms up and it emits infrared light. So our planet emits infrared radiation, which is trapped by gases that are radiatively active in the atmosphere, the things we call greenhouse gases. And these are really a very small part of the atmosphere. Most of the atmosphere is made of nitrogen and oxygen, which are not radiatively active. They don't hold infrared radiation in. But water vapor, all the clouds and the humidity and so forth, and carbon dioxide do. So water vapor and carbon dioxide have been around and part of our atmosphere for billions of years. Their presence results in an average surface temperature of approximately 60 degrees Fahrenheit rather than the 5 that would be there if we didn't have water and CO2 in the atmosphere. So what's the problem? And the problem is the increasing amount of CO2 and other greenhouse gases in the atmosphere. I showed you, a lot of times what I do at this point is ask people when they thought that the scientific world first suggested that global warming would take place. And those of you with sharp eyes saw that it was really quite a long time ago. And it was based on theory, not observation. A Swedish scientist, Svante Arrhenius, hypothesized that as we burned fossil fuel, we would add CO2 to the atmosphere and we would raise the planet's average temperature. So this is one of the examples of how basic theory contributes to the formation of these ideas. Now, he was focused primarily on burning coal and on transportation of other sorts, but of course our use of fossil fuel transportation, the increasing population and the amount of CO2 going into the atmosphere led people to think about this as time went on. However, 90% of the carbon of any sort, organic carbon, coal, oil, CO2, anything on the surface of the Earth is actually in the ocean in the form of bicarbonate ion. So while Arrhenius suggested this, most scientists said we don't have to worry about it because there's so much bicarbonate in the ocean and it's in chemical equilibrium with the atmosphere that anything we put into the atmosphere will be taken up by the ocean and we won't have to worry about it. Here's where we come into the idea of understanding and understanding Earth processes. In the late 50s, an oceanographer named Roger Revelle, who was at Scripps Institution of Oceanography, and his colleagues used stable isotopes and radiocarbon, C14, to understand how much CO2 from the atmosphere would go into the ocean. And they were able to show that only a fraction of the CO2 that we emit from fossil fuel would go into the ocean, and a substantial amount would stay in the atmosphere as a greenhouse gas. So this sort of brings us back to Arrhenius' first idea that CO2 would build up and there would be a greenhouse effect. So this reopened the whole issue of global change due to CO2, which had been essentially a dead issue since the turn of the century. In a very famous paper published in 1957, Roger Revelle said, human beings are now carrying out a large-scale geophysical and geochemical experiment of a kind that could not have happened in the past nor be reproduced in the future. And this was really the modern call to arms to understand what was happening as a result of this tremendous experiment. One of the things that Roger Revelle knew was that in order to understand something that is developing with time like that a third element had to be added, and that was the element of long-term observation. And so he convinced, at that time, a young scientist from Scripps named Dave Keeling to begin measuring the concentration of CO2 in the atmosphere from a place that would he thought, average CO2 for the entire northern hemisphere, and that was the top of the highest volcano in Hawaii, Mauna Loa. And so in 1958, the first of those measurements started, and they have given us what we now look at as one of the iconic figures of global change, the record of greenhouse gas concentration in the atmosphere. The jagged line reflects the fact that this is in the northern hemisphere, and as you know, plants use carbon dioxide and give off oxygen, and during the winter, they're not growing, they're not photosynthesizing, but during the summer they are. So during the summer, the CO2 goes down as they use carbon dioxide, and in the winter it relaxes back up. So the sawtooth is a result of photosynthesis by plants, and the increase is the result of our burning of fossil fuel as well as our changes in land use. Other gases that are greenhouse gases have increased too. Methane is another greenhouse gas. It's a potent greenhouse gas, but it has about a third of the total effect of CO2. Sulfur is an important gas with a cooling tendency because it tends to reflect light off the top of the atmosphere, and it's been increasing in the atmosphere as well. So it's a very complex mix of atmospheric chemistry that's going on. And as a result of those observations, the understanding of processes, and the theory, we come to our present knowledge of the global CO2 cycle. And that is that every year we put about 6 gigatons of carbon into the atmosphere from burning fossil fuel, from the weathering of cement, and from other processes. About half of that, 3.2 gigatons, stays in the atmosphere, and that's what you see building up in that Mauna Loa curve. About 1.7 gigatons goes into the ocean. It increases the amount of CO2 in the ocean, and many of you have read about the fact that it also is decreasing the pH of the surface waters of the ocean, making the ocean slightly more acid. About 1.4 gigatons goes to land, primarily in the form of plants that are growing, a terrestrial carbon sink. But our land use changes counterbalance some of that and add to the atmosphere as we cut down forests and change land use. I said that chance played a role in this entire issue of how people understand the role of climate change, in whether they're open to listening to it, and what credence they give it. And for this entire time, since 1957 until about a couple of decades ago, this was purely the realm of academic scientists. They were looking at the CO2 buildup. They were using theory, using understanding of processes to try to understand what was going on. And then in 1988, we had one of the most profound droughts and heat waves that we'd had since the 1930s. Terrific droughts in central and eastern U.S. with severe losses to agriculture, $40 billion in damage to crops, $60 billion in total cost when you add the follow-on effects. Worldwide, 5,000 to 10,000 deaths, including heat stress-related injuries. Headlines around the world, but certainly in the United States, about this heat wave. And on a blistering day in July of 1988, Dr. James Hansen of NASA testified before Congress. That's him on the right, next to Steve Schneider, a very well-known climate scientist. And Jim Hansen said, it's time to stop waffling and say that the greenhouse effect is here. And that testimony, which made headlines around the country, together with the chance of that drought, really captured a lot of public sense of this idea that climate could change. And here's the record going from 1850 to 1988 at the time of global average temperature. And that was based on readings from thermometers, not inferences from some kind of other proxy, but measurements from thermometers. And so Jim Hansen was making that conclusion based on this part of the curve here. So there was certainly a lot of attention to this, but also a lot of continuing scientific debate, which was at the time probably well justified. First, the legitimate scientific uncertainty about long-term variability of climate. So was this just a variation that, like the 30s, that would last for a decade or two, and then we'd go down to lower temperatures, that the drought would go away and we would in the West, and that we would have normal precipitation patterns. Also, legitimate scientific uncertainty over the variability of the sun. The sun varies very slightly with time in the total amount of energy and radiance that comes from the sun to the earth. So there was also a legitimate debate to say how much of this is due to very slight changes in solar radiation that have nothing to do with CO2 and nothing to do with greenhouse gases. And why is this so important? It's because we live in a carbon-based energy economy. We burn oil, we burn coal, we burn natural gas, and our economy was so dependent on fossil fuels that everyone was reluctant to try to impose great changes in the emission of fossil fuels if there was this much scientific uncertainty. Now, I think that it's fair to say that the argument on the part of especially Steve Schneider there on the left was what was called the precautionary principle, that if there's a chance that this is the case, shouldn't we be investing in conservation measures and energy efficiency measures which would decrease fossil fuel use, result in savings for industry, and shouldn't the federal government especially mandate that? I won't talk about politics. I'll only talk about observations of political argument. That precautionary principle was not taken up as a way forward for either federal policy or state policy. What was done as a result of that scientific uncertainty was the passage of what was called the Global Change Act of 1990, which mandated a doubling in the funding for research associated with global change. So what did the scientific community do with that? I'll just focus on a couple of things that I think really transformed the debate about global change. And the first of those was the investment in analysis of cores of ice from glaciers and also from Greenland and from Antarctica. And these slides show scientists, in this case at the South Pole, drilling a well and putting a core down into it and pulling up a core filled with ice. And here's that ice. And within the ice, there are trapped bubbles of atmosphere. So as that ice freezes, just like the bubbles that you see in the ice that you make in the refrigerator, there are bubbles of air that are trapped inside of it. And they're frozen in, and more ice develops on top as a result of the accumulation of snow and the pressure and the conversion of that snow to ice. And so those bubbles trap the atmosphere of the past. And with time, a tremendous amount of effort was put into understanding all of the physics of bubble formation, all of the chemistry of equilibration of those bubbles with the ice around them, and analytical capability to melt the ice in a clean way with no contamination from today's atmosphere to be able to analyze the atmosphere of the past. And so we developed impeccable scientific measurements that show that greenhouse gases are increasing in the atmosphere. So this is a record from bubbles formed in ice 1,000 years ago to those near the present. And it's the abundance of CO2 in parts per million by volume. And they show that for much of the last 1,000 years, the concentration of CO2 was around 280 parts per million. Starting at about the time of the Industrial Revolution during the 1800s and increasing to present, CO2 was increasing in the atmosphere. And the little line here at the end is the instrumental record with that arrow. So a 31% increase in CO2 in the atmosphere over the industrial era. So I've blown up that atmospheric CO2 curve so that you can see that this portion from about 1850 on is from thermometers, and this portion in the past is from ice cores. And there are portions where they overlap so that we know that the ice cores are giving us the accurate representation of what, I'm sorry, this is the CO2 curve, not the temperature curve. So here from about 1950 on are CO2 measurements from Mauna Loa, and everything else is from ice cores. And there are portions where they overlap so that we know that the two are congruent. We also know, using these ice cores, that we can go back hundreds of thousands of years into the past to understand what CO2 was like during the great changes in climate that came as the result of the ice ages. And what I have here is another plot that shows the CO2 from ice cores. And I apologize, this is the other direction. Now, old is on this side, and young is on this side. And that's 160,000 years ago, up to present. And it's thick, the line is thick because I'm showing you the total error on the measurement of CO2. And the last glacial maximum, the last time of maximum ice volume on Earth was about 25,000 years ago. So that's at this, if I can get there's the arrow back. That's at this portion. The last interglacial time, the last time when it was nearly as, or actually a little warmer than it is now, is back here about 120,000 years ago. And so the CO2 has changed that much. But you'll notice that the maximum during any of this time was about equal to the pre-industrial CO2, about 280 parts per million. And we had increased 31% since then. Interestingly, the top is a measure of the relative temperature change over the same time, and it's calculated from the isotopes of deuterium, a heavy water isotope, or a heavy oxygen isotope in water that is directly related to temperature. And the thing that you can see is the close relationship between temperature and CO2 over the past 160,000 years. And if we look at an even longer record, and I apologize that the figures keep bouncing back and forth between where the present is. In this case, old is on the left, today is on the right. And this isn't just the one glacial cycle, but many glacial cycles over the past 500,000 years. Antarctic surface temperature in red, pre-industrial atmospheric CO2 in blue are closely related. And then in green, you can see where we are compared to the past. So the CO2 is unprecedented compared to any of the glacial ages of the last 500,000 years. So, we know about the past. We have a relationship between temperature and CO2 in the past. How about the future? How do we say anything about what our current CO2 increase will say about the climate? How do scientists make predictions of this sort? They base them on models, and that's the fifth of those 5 factors that I talked about. Theory, understanding processes, long-term observations, models, and of course, chance. So this is a cartoon of the climate system. It has, of course, solar radiation, the atmosphere, the hydrologic cycle, all that water that is a greenhouse gas, the human influences and the CO2 coming from our burning of fossil fuel, vegetation, the ocean, the ice. And so the challenge for scientists is to put together a model that can incorporate changes in all of those systems and predict the future. And that is a formidable challenge. And so this is a very simplified cartoon of the things that modelers include in global climate models. So each one of those boxes is the concentration of something or measured variables. The arrows would be equations that would talk about the physical exchange or the chemical exchange of energy, of material species, and so forth, and trying to understand how to put all of that together into a mathematical representation of the present climate, and then force it to change with increasing CO2. Our understanding of these models is dependent on our understanding of processes, and it's also dependent on our long-term observation of how all of these processes change with time. Between 1990, when the Global Change Research Act was passed, and about 2000, there was, in addition to this flowering of observations of CO2, there was a tremendous flowering in the capability of scientists to represent the climate and processes on Earth with mathematical models, partly as a much better understanding of processes, certainly as a tremendous increase in computing power, and as that computing power increased, scientists were able to put more and more aspects of the Earth system into the models. When you don't have much on your PC, you could probably do a model that included just the atmosphere, the CO2, the water. But you would never be able to include the ocean. There's just not enough power to do all of the calculations all at the same time. So as compute power increased, the sophistication of the models increased. So in around 2000, the first results of very broad-scale climate models started to come out. This is an example from the Hadley Center in the UK, and it is a representation, their calculation of what the average surface temperature of the Earth would be in 2100 given our present rate of increase in CO2. And those dark red colors at the top represent an increase of about 3 degrees centigrade, or close to 7 degrees Fahrenheit. You'll notice there isn't anything that shows a decrease. So these were, at around 1998 to 2000, very scary kinds of models for what we might be looking at if we continued to use fossil fuel at the same rate. Now, I told you that water was another greenhouse gas, and it was very much affected and very much a part of climate. So this is a model from the same simulation that shows the precipitation change over the Earth. And you'll notice, again, for 2100, and you'll notice a band of blue of greater precipitation along the equator, and on either side of it, bands of much lower precipitation in the dry areas of Earth. So the conclusion of the scientists was that the extremes of climate, the extremes of precipitation, would increase as a result of CO2 and global change, not just global warming, but changes in climate in general. Now, why didn't everybody just say, okay, done deal, let's go and precautionary principle, let's legislate this and so forth? One of the reasons was that those models still did not have a lot of capability of directly mimicking the change that we had seen over the last 100 years or so. And this is a graph from about that time. And on the left-hand side is 1860. On the right-hand side is 2000. The black curve was the observed surface temperature. It's listed here as an anomaly. So they took the average surface temperature for the last 150 years, and then they showed it as an anomaly compared to that. So that's the real record of temperature in black. The red is the climate simulation. In general, they're the same. There's an increase in temperature in the model. There's an increase in temperature in the observation. But the details of it were not very good, and the timing of when things would happen was not very good. So depending on your politics, you could say the scientists have a general idea, they have a theory, but they haven't proven something that would force us to change national policy about greenhouse gases, potentially costing a lot in corporations retooling, potentially costing a lot in increased price of gasoline, causing massive changes in the use of fossil fuel. Or if you were a person who liked the precautionary principle, you might say, well, squint, and they're really, really very similar, so what are you waiting for? So this was really the situation about 7, 8, 9 years ago, with a difference of opinion about how to act. Around that time, those governments that felt more strongly that the case had been made started negotiating an international agreement called the Kyoto Protocol. It was an international agreement on how the world's nations would seek to decrease greenhouse gas emissions through 2012. So a 15-year horizon. And the essence of the agreement was that the developed world, which is responsible for most of that CO2 emission, would cap its emissions and would say, okay, we won't put more greenhouse gas into the atmosphere, or at least there would be a very small amount of increase that was allowed. And the developed world would offset any emissions where if we couldn't keep ourselves under that cap, we would offset that by buying carbon dioxide credits for undertaking clean development projects in the developing world, i.e., we would invest in development in the developing world in projects like hydropower, wind, biodigestion of methane, capture of methane from pig and cattle farming, from rice, and use that methane for energy. Much of the world didn't think much of this mechanism, and if you go onto Google and put in Kyoto Protocol and look for images, you will get some of the most amazing political cartoons that you have ever seen. This is a wonderful example. It's Kyotozilla, and for those of you who can't see it, this farmer here with the hat in the right is saying, wow, it's crushing Alberta's economy, trampling our jobs, flattening everything. What a great movie. And the politician is saying, that's not a movie. And so many parts of the developing world said, we can't adjust to this. We can't accept these caps. And we knew, even during the late 1990s, that it was clear that the U.S. Senate would not ratify the Kyoto Protocol. So there was never any question about the U.S. ratifying the Kyoto Protocol, but we were part of the process. That was, we declared ourselves to be part of the process, and we kept negotiating for more advantageous accommodation in the caps, more advantageous accommodation in offsets and so forth. In 2001, President Bush, largely in response to a political position that said we don't want to undertake these restraints on the U.S. economy when the economies of the developing world, primarily India and China, can continue to grow apace and don't have to cap their emission. And in addition to this, Kyoto would require us to spend a tremendous amount of development money in China and India. So right now, about 65% of the clean development activities that go on as a result of Kyoto are in China, 18% are in India. So this was also viewed by those who didn't like the idea as a massive transfer of development funds from the U.S. and the developed world to China and India, further increasing their competitive capability. So I think, again, we're not talking about whether you like or you don't like a particular point of view, but it's important to understand the basis for what was making people so nervous. Around this time, the third assessment of the Intergovernmental Panel on Climate Change, a UN-mandated activity in which the scientists of the world look at, they don't do research, they look at everybody's research over the last 5 to 6 years, and they assess the state of our understanding based on that research. So it was the third assessment in 2001. And for the first time, in addition to the CO2 evidence that we had, increasing sophistication of the models, we had the first detailed 1,000-year record of northern hemisphere temperature. This was taken, the red part of the curve. So old is on the left, young is on the right. So 1,000 years of history. The black, let's start with the red. The red are the data from thermometers since 1850, showing that increase. It looks much more precipitous here because we have a longer time frame. The blue line and the black is an average, is the data from tree rings, ice cores, etc. So those aren't direct measurements of temperature, they're indirect measurements of temperature. And the gray is the error bar on that. And so the conclusion was, and this became known as the hockey stick diagram because of the long handle and the abrupt shift. So the hockey stick diagram of temperature change. Those who wanted a call to action said, look at what's happened. We had a long, slow, somewhat decrease in temperature, and then a very abrupt change since we've started putting a lot of CO2 in the atmosphere. Those who were more skeptical said, look at the size of the error bars there. And they become very large because this older part of the record is based on a very few samples, tree rings, and the relationship of tree rings, precipitation, and temperature. And there aren't that many trees that are 1,000 years old. So when you get to the very end, you're probably talking about 10 to 15 samples. Whereas over here, you're probably talking you're hundreds of samples. So people who were concerned about pushing science too far said there's too much error in this, we don't believe it. Those who, the people who generated the diagram said, look at the statistical errors in the past, and we're way beyond those. It's time for action. For the first time in 2001, we also had sufficient records of the measurements of temperature in the ocean to look at 50 years of oceanic temperature. And these temperatures are from depths of about 1,000 meters in the ocean. So they're above the level that's influenced by weather. They're longer-term averages. And so that's from 1950 to 1995 in each one of the panels. And you have going from the top left, the South Atlantic, the North Atlantic, then the South Pacific, North Pacific, and the Indian Ocean, and the world. So the conclusion of the oceanographers was not only is the atmosphere heating up, but it's affecting the ocean as well. And why is that important? Because water expands as it heats. So this was going to increase the volume of water in the ocean, and even though it's a very small amount, when you get close to the shore, you have a very gentle slope, and sea level would rise. In addition, a longer-term record of precipitation events was developed. And this is, again, from weather records. The percent of the continental U.S. with a much above normal precipitation from extreme events. This was the first time that we saw the climate change community start talking about not only gradual change, but the impact on extreme events. And so from 1900 on the left to 1990 on the right, an increasing trend toward more precipitation coming from extreme events. So you've heard a lot about that over the last 5 years, the potential for more storms, for heavier rainfall, and this is the scientific record behind it. So this is the cover of Time magazine, April 9th of 2001. We had the U.S. saying we weren't going to be part of Kyoto. We had the Intergovernmental Panel on Climate Change reporting out in January of that year with all of this data. And so the headline is, Climbing Temperatures, Melting Glaciers, Rising Sea, All Over the Earth We're Feeling the Heat. Why Isn't Washington? And this, I think this time really began the great debates over climate change. This is the time when the rubber hit the road politically, and we started seeing people take a political stand on whether they believed the data or whether they didn't believe the data. In most cases, people were willing to accept fact, like the increase in the precipitation extremes, but they weren't willing to have that explained by the models, this attribution of CO2, because they didn't feel that the models were good enough. And the words that this report used, the IPCC report, was that it was likely that these changes were due to human activity. Likely was a word with a specific statistical definition, and that was 60 to 90%. So if you didn't want to change, you said 60%, If you thought, this was a call to action, you said 90%, it's our fault. I'm going to jump from there to 2006 because most of you have started really hearing a lot about this in the last couple of years. And in part, that is because we all knew that in February of this year, the Intergovernmental Panel on Climate Change would issue its fourth report. So they would summarize everything that had happened since 2000, and we would have another look at this question. And so you've seen a lot of attention to climate change in the last year, sort of as a run-up to those conclusions. Obviously, Gores Movie, An Inconvenient Truth, which was essentially like this, a PowerPoint picture of the data that was out there. The data that was included in Gores Movie is data that was familiar to all of us in global change. It was heavily vetted. Nobody disputes that. There were, however, many conclusions that were drawn from that, and so skeptics again said, this is overinterpretation of the data. Shortly after that movie came out, another type of report came out, and this was the Stern Review on the Economics of Climate Change. Sir Nicholas Stern was the former Chancellor of the Exchequer of UK. So he was like the head of Treasury at UK. He's a formidable economist with an impeccable record of understanding economy, economics, and the way that various variables go into economic projections. The Stern Report was a 700-page document. It was an economic analysis of everything associated with global change, primarily from the standpoint of impacts and the standpoint of costs of action. And Sir Nicholas Stern said, climate change threatens to be the greatest and widest-ranging market failure ever seen. Now, what does he mean by that? He means that the cost of climate change is not embodied in the cost of fossil fuel. So in buying oil, you don't pay for what the potential impacts are. So the market doesn't really reflect all of the cost of the product. And that's what he means by a market failure. He further said our actions over the coming few decades could create risks of major disruption to economic and social activity later in this century and the next, on a scale similar to those associated with the Great Wars and the economic depression of the first half of the 20th century. Scary words from a Chancellor of the Exchequer and an incredibly well-known and well-respected economist. He called for an investment of 1% of the gross domestic product of the developed world to avoid costs which he estimated to be 20% of the gross domestic product in the future. So this was the first time that an economist had looked at this in a cost-benefit analysis. But there are still it's still a matter of the models that you use. 3 Nobel Prize-winning economists praised the report and called for action. Many governments called for action. Other economists, including a Nobel Prize winner, challenged the discount rate set for the cost of action and said it doesn't add up. You've discounted the cost of what the action that we would take now compared to the value we would get in avoiding problems in the future. So basically they were saying you've underestimated how expensive it will be to do this, and whether or not we believe that we should do something, it's going to cost a whole lot more than this. Nonetheless, this was the first time that this sort of analysis and assessment moved out of the scientific realm and into the social sciences, the science of economics. And on February 2nd of this year, the IPCC fourth assessment report highlights came out. The full 400-page document won't be out for about 2.5 more months, but we already know the key conclusions. First of all, they said now the scientific community is saying climate change is unequivocal. These are scientists. There are 2,500 scientists who participate in the IPCC process. Any of you who have had anything to do with scientists and getting them to give you an opinion about something would know that they almost never say anything is unequivocal. And in this sense, again, it's a term with a very specific definition, and it means greater than 98% certainty that climate change is happening. And also, most likely, another statistically significant term, greater than 90% likelihood that the changes are due to our activity. So this is really what many people have called the smoking gun, or the unavoidable evidence from science that it is our fossil fuel use and our land use change that are resulting in climate change. In addition to this sort of nailing down, okay, now we really believe, two things were really impressive to scientists. The first was that the report says that changes in the polar regions are happening much more quickly than anticipated, and that we have doubled the rate of temperature increase since 2001. So we're increasing the temperature even faster than we anticipated before. So the latest version of the data here from time 10,000 years ago to present with CO2 and the continuing increase in CO2. And now on the top, the global average temperature curve as of 2005. And so now it's much harder to argue that this is just a decade-long change or even a 20 or 30-year change. So that's 1850 to 2005. I put a bar on there to go back to where we were in 1988 when Jim Hansen first said it's time to stop waffling. And I think that you can see a justification for the greater amount of certainty that the IPCC has accorded this. In this tremendous conclusion about the rapidity of change in polar regions and in glaciers, there are models, again, far superior models than we had in 2001 about what the temperature change will be in the future. The line down the middle here is 2000. So this is known temperature change. The curves here are the results of different scenarios of fossil fuel use out to 2100. The yellow on the bottom is what would happen if we never put another atom of CO2 or another molecule of CO2 into the atmosphere. If we just stopped any kind of CO2 increase, we're still committed to some temperature increase, and it wouldn't go down right away. The red is what's called the business as usual scenario, and that's just we go ahead and we keep burning fossil fuel at the current rate. And the blue and the green are different models of the degree to the speed at which countries cap CO2. The models in terms of temperature change for the future are equally stark, and this is The little maps on the right-hand side, the sort of yellow and green ones, are the projections of surface temperature for 15 to 20 years from now, 2020 to 2029. The ones on the right hand that are more red are similar to the one that I showed you before for 2100. And it doesn't matter which of the models you look at, whether they're more conservative about the impact of CO2 or see more impact. We're looking at temperature changes, especially in the polar regions, of up to 3 degrees centigrade or nearly 7 degrees Fahrenheit. And again, dramatic changes in the patterns of precipitation. Those blue colors at the top and bottom are 20% changes, relative changes in precipitation. The red and brown colors are 20% the opposite way, drying. So again, tremendous changes in the distribution of precipitation and attendant changes in agriculture. So what is still uncertain? What research is necessary in a world that's so aware now of what's happening? First, an understanding and modeling of ice sheet dynamics is one of the most challenging aspects of climate models. This little picture is a picture of Greenland, and it's developed from satellite imagery. The blue colors are places where the ice is melting at a very rapid rate. It's retreating by up to 60 centimeters per year. But look at the middle of Greenland. Those brown colors are an increase in the height of ice by almost 60 centimeters a year. So change is taking place, but what's going to happen? Will the melting at the edge sort of result in essentially lubrication of the ice sheet and a lot of dwindling of Greenland, or will it continue to build up? You know, a big uncertainty in this whole issue. The deep circulation of the oceans is critical to long-term climate stability. The oceans are the big flywheel of climate. They have incredible heat capacity, and they hold a lot of the heat on Earth. And these squiggly red and blue spaghetti lines represent, in red, the main surface circulation of the ocean, and in blue, the deep water circulation. So what happens is, in general, water moves up the west coast of South America and North America. It goes up to the polar regions. It gets colder and therefore denser. It sinks and moves down, moves down the western coast. So this is a big overturning circulation of the ocean that modifies its temperature with time. We know very little about how this will change with time, but there is now evidence that shows that the areas in which this bottom water forms have changed remarkably in the last 50 years, and those colors are the salinity contours. And why is salinity important? Because fresh water is less dense than salt water. And so if the water is much fresher as a result of precipitation and melting of ice, it's harder to sink. And there's concern about what that effect that has on this big overturning circulation of the oceans, a major uncertainty for the future. Impacts of climate change, very difficult to model, whether they're health impacts or agriculture, forests, coastal zones. And understanding the impact on sea level is a major uncertainty. I told you that as the ocean warms, it expands, sea level can rise. As ice melts that is on land, it contributes to the height of the ocean. So sea level, if all of the ice melted in Greenland, and would result in a 1.5 meter increase in sea level. If all of it melted in Antarctica as well, it would be a 3 meter rise in sea level. And we would see major changes to the coastal zone. We've heard a lot in the last year about various other kinds of impacts. In Washington State, the pine bark beetle is a major predator or major influence on the vigor of the pine forest. And its concentration is very closely related to precipitation and drought, all of which are very strongly influenced by climate. So I'm not saying that we're in the midst of a permanent change here. What I'm saying is things like this are very much influenced by climate, and we have very little ability to understand them. So, in light of all this, is the U.S. responding? In the last year, we've seen California enact legislation calling for a cap to greenhouse gas emissions in California. Remember, California on its own is the 6th largest economy in the world. So if California does this, it's a major influence on carbon emissions. A regional greenhouse gas initiative by New England and by Mid-Atlantic states is also projected to cap greenhouse gas emissions. And 2 weeks ago, a group of 10 of the largest U.S. corporations joined 4 environmental organizations calling on Congress for a cap-and-trade system. Cap the emissions and let us trade amongst ourselves. If we have less emission, we'll trade to somebody that has greater emission, and then gradually decrease those caps. 6 international corporations have said that they will become carbon neutral voluntarily, i.e. that they'll have no net carbon emissions by 2010. And the day before yesterday, Branscombe, the CEO of Virgin Airlines, announced a $25 million prize for the individual or corporation that can successfully remove 1 billion tons of CO2 from the atmosphere per year. That's 1/6 of the current amount added to the atmosphere each year. So a lot is going on, and as a result of these incredible changes in the last year, although there is still much uncertainty about the impact on you and me and on our local view of climate change, we're beginning to see tremendous changes in the acceptance of the idea and the ability of companies to accept a precautionary principle that they should take action. So I'll end with this wonderful quote from Aldo Leopold, one of the true environmentalists of the last century. The first rule of intelligent tinkering is to save all the pieces. And, of course, he meant save the pieces that make up this wonderful blue marble planet that we live on. Thank you.